Good afternoon. In today's lecture, which will be a little shorter than usual, we'll talk about conformational analysis. We already touched upon conformational analysis when we discussed free rotation around a single bond. So at that point, we started grasping that the concept of structure is really a multi-layered one. For example, if you look at the structure of ethane, we may imagine something looking like this. And this structure would be something we would describe as composition. But implicit in this structure are at least two more detailed representations of ethane structure. One of them would be this eclipsed structure, while the other could be the staggered structure shown here. Now, these two structures are really they're quite different from the concept of composition, because the composition of ethane doesn't change. What changes is its conformation. And conformations of ethane are structures of ethane which are related to each other by rotation around a single bond. So no bonds need to be broken or formed, no atoms need to be added or subtracted. We only need to do a simple rotation on a single bond, or multiple single bonds, to get from one conformation to the other. Now, this appears like a very intricate subtlety of structure, but in reality it's not. Issues of conformation are very relevant in physiological function of many naturally occurring compounds, as well as in reactivity studies that we're going to get into later on in the course. And so we will, in this lecture, talk about conformations of several simple alkanes and see how things change, and our analysis will be quite detailed and will focus on energy differences between different conformations. To begin that off, we will start with a molecule which actually has no significant conformations, and that is methane. So even though methane has 4 single bonds, rotation around these single bonds is virtually undetectable because we cannot, hydrogen atoms are spherically symmetric, so we cannot see if they're moved or turned or not. And so methane, for all practical purposes, is a perfect tetrahedron with an angle of 109 degrees and 28 minutes between each pair of its CH bonds. And those bonds have a bond length, which is another important parameter, of 1.09 angstroms. An angstrom is a unit which is a little archaic, but it's being used for bond lengths quite routinely. 1 angstrom equals 10 to the minus 10th meters, or so that means that this structure could be, this number could be converted in 0.109 nanometers to bring it into a systematic unit. So as I said, methane has no conformations because the rotation around its single bonds cannot be studied. But next higher homologue, ethane, will, and we will get into that in the next topic.